Hello, adventurers, and welcome to Floor 7, the Cisterns. Take your number. I will see you in order. There is no other. Past Cantor Resh's lectern, the corridor turns and slopes down. The walls grow slick. Somewhere ahead, water. A low, regular drip with the cadence of a clock. The corridor empties into a low, ceilinged hall floored with painted tiles. Red then blue, red then blue, that mark out a single, very long line. At the far end of the line, behind a low ironwood desk, a clerk monk in a soaked gray robe waits with a stamp in one hand. Petitioners stand in front of him, one after the other, and he sees them strictly in the order that they arrived. No one cuts, and no one is skipped. The cantor behind you remembered the last word spoken. The steward in front of you remembers only the first petitioner still waiting. Steward Quill, the keeper of the cisterns. I will see you in the order which you arrived. No sooner, no later. The petitioner at the front of the line is the oldest unanswered petition. When I am done with them, they leave. The next oldest steps forward. The line shortens by one. There is no other way to keep order. Cantor Resh upstairs remembers the last thing said. I remember the first thing still owed. Both of us are right for different problems. Bring me your problem. So, what we've been working with in recent times has been dealing with the most recent items. When you think about dealing with push and popping, touching the same end of our chain, and the lesson was really LIFO, or last in, first out. In terms of this floor, the contract is going to actually flip. We're going to push at one end and remove at the other. The oldest waiting element is the next one that is going to be served. This is what we call FIFO, or first in, first out. The line at Quill's desk is the most ordinary data structure in the world, that which we call a queue. So it's the shape of every fair waiting room that's ever been built, or the line you stand in to get your coffee at Starbucks. And so what we're going to work with this week is we're going to deal with our stack from floor 6. We're going to wrap a chain with a push front and a pop front. And then we're going to have our queue of type T that's going to wrap the same chain that will have a push back and a pop front. Okay. Now, so really just one word change here. Our contract is going to flip from LIFO to FIFO. That whole contrast is really a whole lesson on what an abstract data type actually is. It's not the code. Remember, it is the promise. Okay. Now, one thing, FIFO is going to be the other side of our LIFO coin. So push and pop on the same end is a stack. Push and pop on the opposite ends is a queue. Okay. Queues are going to be how things stay fair for us here. So think about print jobs, network packets, threads, browser tabs. Anywhere where we have to honor the order in which a request has arrived, a queue is going to be the thing that does your bookkeeping for that. Okay. You can also think about classic exercises, hot potato. Right? Pass a token around a circle and eliminate every kth person. You can almost kind of think about that as drilling an example. And now a queue, of course, is going to be half of a tree traversal that we have not written yet. In 3 floors from now, we're going to actually walk a tree in breadth first order, dealing with our closest nodes first, and then we go on to next closest, so on and so forth. The data structure that's going to make this possible is going to be a queue. Each of our visited nodes will enqueue its children, and the children come back out in the order they were enqueued. So today, we're going to start by writing our queue. And so you kind of see here this little queue in repose here. So we have a dequeue and an enqueue, and notice how we're on different sides of the chain here. You can notice here when we enqueue, we add B, add C. We then dequeue. You notice then A pops off, dequeue B, we pop off B, and then dequeue C, we pop it off. Okay. And then another thing we see here, same chain but different end pairing here. So you notice here with the stack, right, it's last in, first out. We push and pop there together at the head. Meanwhile, here with the queue, we dequeue from the head and we enqueue on the tail. Okay. Now, here is loading up our floor 7 material here. Now, when we think about with floor 7, the cisterns, upstairs, Cantor Resh remembered the last thing we said, right? That was our stack, last in, first out. Down here, Steward Quill will keep a orderly line. He sees petitioners strictly in the order that they arrive. The front of the line is the oldest one still waiting. Okay. Now, let's go ahead and run this real quick. I want to show you kind of where we're starting at with our code for this this module here. Okay. I'm going to self-test. We now have a new command, self-test, on the queue. Okay, so you notice here we have an empty queue is okay. Then notice we have an enqueue. We fail. Enqueue is a no op. We need to wire our enqueue. You know, so you have several different fails here. So we obviously got some things we got to go fix here today, right? Now, phase 1 is green, but that's really a live omission here. An empty queue reports size 0 and empty true by accident because the stubs return 0 and true. Phase 2 through 4 are red. Our enqueue did not grow anything, and our front didn't return the first thing in. dequeue did nothing. The storage works. It's the same floor 4.5 chain fundamentally underneath. What's missing is the promise, and this time the promise points at the other end. So what we need to work on here, first of all, is we're going to go and work in the hero/queue header file. Is going to be where we'll work first of all. Okay. Let's go ahead and let's pull that up here. Let's see, where's that? There's the queue header. Okay, perfect. Now, what we're going to deal with when we think about for this floor's content, in the first video here, we're going to work with our queue as an adapter. So we're going to work with 4 one-line methods and then get our self-test on our queue to go green. Okay. Then the whole trick here is really going to be which end each one of these methods touches. Okay. In the next video, the canonical thing we do with the queue is we're going to do hot potato. We're going to pass a token around a circle and eliminate every kth person. And then the last video, we're going to drain an enemy line in arrival order. And then we're going to do a classic interview puzzle as well. We're going to build a queue out of 2 stacks. So by the end of this floor, you'll have written the same 5-line adapter twice in 2 weeks, and you'll know in your bones that the ADT is the promise and not a pile of code. Okay. Now, let's go ahead and let's go to, in this queue file here, let's go ahead and let's read here. Here, okay, so right here we have our T front here. I want to just kind of walk through this section here. Front is already going to be written for us. Both overloads, 1 line each. And so if we notice here, I also left a comment here for you as well. Front returns a reference T ampersand and a const T ampersand for the const version, not a copy. You cannot honestly stub a reference. There's no safe placeholder T ampersand to hand back before enqueue works. Any value we return would either be the real answer or dereferencing of a null pointer. So the starter here gives it to us, exactly like floor 6 gave us top, and for the identical same reason. Now, if we look at the body and put it next to last week's stack top, it is the same line, the chain underscore dot head accessing the data, the head of the chain. Here's the beautiful part, though. Nothing physical changed. In our stack, the head was the most recently pushed item. In our queue, because we'll enqueue at the back, the head becomes the oldest item still waiting, which is the front of Steward Quill's line. This is the same geography, just opposite meaning. That's essentially the whole floor in one unchanged line. Okay. Now, let's go ahead and do our enqueue here first. So I'm going to delete what's in here, and let's fill this thing out. So we're going to say, of course, it takes a const T ampersand value. We're going to say chain underscore dot push back of our value. Okay. So enqueue is pretty simple. It's a 1-line process here. Now, the whole reasoning, though, is really the lesson for us here. A new petitioner joins at the back of the line. So we push at the back of the chain, right? Pushback is big O of 1 on our doubly linked chain because it has a tail pointer, okay? It splices a node on at the end without walking anything. And because front actually reads the head, the thing we just added sits behind everyone still waiting. It will not be served until all of them are gone. Once again, that is FIFO, first in, first out. And now here's a trick or a trap, and it's Grix's favorite shortcut. If you got, quote, clever and used push front here, you would jump to the front of the line. You would have rebuilt a stack, last in, first out, without really noticing it. The self-test will catch that exactly in phase 3. Front would hand back the thing you just added instead of the oldest one. The body is trivial here. The choice of which end is the entire job. Now for dequeue, we want to remove, of course, from the front. So really for dequeue, it can be void. We just need to make sure we say chain pop front as such. Okay. So dequeue removes the one thing being served. Removes the one being served. I apologize. The front, which is the oldest, so we pop from the front. Notice the asymmetry we just created. Enqueue touches the back, dequeue touches the front, which is opposite ends. That one asymmetry is the whole data structure in action here. Compared to last week where both push and pop hit the front, same end, of course, that being the stack. Now, 2 notes here, same as the stack for us. 1, dequeue returns void. It does not hand you the value. You read the front with front and then dequeue to discard it. 2, our pop front is a safe no-op on an empty chain. We built it that way in floor 4.5, so dequeue on an empty queue won't actually crash your program. Front on an empty queue is the one that bites, and we'll meet that hazard head on in the last video for this floor. Now for size and empty, see where size and empty is probably down here towards the bottom, ain't they? Yeah. Okay. So we want to be able to return the size of the chain. So we'll return back our chain underscore dot size. Okay. And then for our empty, our bool empty, we're going to return our size equivalent to 0. Okay, so there they both are right there. Now, size forward straight to the chain. Empty delegates to our own size. Empty is just the size equals 0. No need to ask the chain twice there. These two are byte for byte identical to the stack versions. If you open stack in the header file and look, they're the same. As you may ask, someone may be thinking here as they're seeing this video, if they forward, why do they exist at all? Because the answer would be the QADT promises them. A caller asks q.size without knowing or caring there's a chain underneath. And if we swap that chain for a maybe dequeue from the standard library tomorrow or next week, these 4 bodies would change and the queue's promise would not. Okay, so that gap between the interface and the implementation is why the word adapter is used so much and why it's important. So let's go ahead and let's build this. So we'll run this here. Okay. All right, so let's run our self-test on our queue. And notice here we get 4 okays, and then we get the final one that says everything's good. Or was that 5? 1, 2, 3, 4. Oh, it was 5. Oh, I was right the first time. Yikes. So all 5 phases now are green. Enqueue grows it, and look at phase 3, the one that matters. After enqueuing 1, 2, 3, so you notice that front returns 1, right? Yeah, so you see here, right here on this line right here, front returns 1. Sorry, I was looking at the line above me there, confused myself. So front returns 1, the first one in. That is the line that proves this is a queue and not a stack. Last week, the same phase proved the top return 3, which is the last one in. So one word, push back instead of push front, flip the entire contract. After dequeue, the front is 2, the oldest is gone, the next oldest steps forward. This is Stuart Quill's line exactly, okay? And so that's the, when we think about, if you wanted to see something, we could as well. So notice here we have size 0, empty, okay? We enqueue 7, of course, size is 1. We enqueue 1, 2, 3, size is 3, front is 1. After dequeue, size is 2, right? So we kind of see, that's fine. But What if we went, just as a little demo here, let's go to our main.cpp right here. And I'm just going to kind of in our main line right here. Yeah, I'm just going to right here. I'm just going to plug something in here. I'm going to say standard queue. I'm going to say, oh, whoa. I don't like it when some of this Visual Studio gets a little too excited there on us. We'll say standard queue of queue, and we'll say queue.push 1. We'll say queue.push 2. We'll say standard cout. I'll say queue.front. Okay, which this should print 1. Okay, let's see, what are we missing up here? So we need to include queue in our header here. Let's go back to main. That should be good there. Yep. Okay. Let's just build this here real quick. And this should print out 1 to us. Yep. So you see we get a 1 back there with our little demo there. So that's the real queue from the standard library. We push 1, push 2, front is 1, first in, first out. We just wrote by hand the same class the standard library ships on the same chain that we built 2 floors ago. Or from the standard library, queue wraps a dequeue from the standard library. Ours wraps a chain. Same promise, different storage, and we wrote a stack the same way last week. That's not imitation, that's the pattern, and you now own it twice. So I hope this was helpful, and I will see you adventurers in the next video. Talk to you soon. Bye-bye.